Hello everyone and welcome to this first video of this TEAM-NANO Educational Lecture Series. My name is Heinrich Lanthaler. I'm a postdoc at the University of Southampton, and as mentioned in this very first video of two in the educational series about electronic textiles, we are going to make an introduction to this electronic textiles. Specifically, we are going to find an answer to this very question: can we make our clothes smarter? Without further ado, let's dig a little bit deeper into what we're going to discover today. Specifically, we're going to give some definitions. We're going to understand what actually are electronic textiles, but most importantly, we are going to learn how we can actually make the electronic textiles we are interested in. But let's start from the very basic concepts. So if I would like to ask you, what are electronic textiles? Well, in order to give me an answer, you should think about uh, fabrics with embedded digital components, basically sensors, microcontrollers, LEDs, batteries, able to interact with their environment to sense data or simply light up, as you can see also with this very nice pictures here reported. Let's briefly make some distinctions between smart textiles. So basically, the textiles are capable of sensing stimuli from the environment, from the surrounding environment. The stimulus can be electrical, thermal, chemical, magnetic, or from the other origin. And basically, the sensing element is integrated in the textile structure. On the other way around, we have the wearable computer, which is an embedded data processing system in the very textiles we fabricated. The input data basically is the output of the sensor, and is basically processed in this very unit. The output is recorded constantly, no matter the particular task or the body position. Having a look at the integration of this electronics, we do have three levels. Specifically, we can start from the very basic one, uh, based on conductive yarns and fibers, in which basically all the cables and connecting system are replaced by conductive yarns and made out of textiles basically. But all the sensors, actuators are made out of bulky material and pretty much standard. The second level of integration is basically based on the possibility to use as a sensitive element or as an actuator the very textile. So the textile itself become a sensor, and it plays an active role in the whole electronic system. Finally, the idea is to aim for an entirely logic board and with all the electronic components made out of textiles. Having a look at very briefly at the history of electronics textile, we have to go a little bit, back in the days with this Qing dynasty in China, 17th century, when they were actually able to fabricate an abacus and to embed this abacus into a ring. Coming up to something closer to nowadays, the very first electronic wearable computer was developed in the USA in 1961 by Edward Thorp, followed in the early 90s by Steve Mann, who's considered the father of the eyewear computer in Canada. In the early 2000s in Belgium, Koosmans and other were actually able to fabricate the very first wireless electrocardiogram system in a textile, which basically became a business. I decided to report here this Mayan um, company based in Canada, which is basically capable of commercialize this scheme. This is a basically a band we are able to apply on our chest to measure some human health parameters. And basically coming to nowadays, the smart textile serves more for extended reality purposes. Specifically, the idea is to aim for either sensors or actuators for better experience in the extended reality. Let's go to the second question of today's lecture: how we can actually make our electronic textiles. Well, let's start from the very basics. Let's build our own building block. So we have to start, of course, from the textile choice. Based on this very textile properties, we have to design the electronic we would like to embed in this very platform and to code this electronic. We have to choose the material involved in the fabrication process. Of course, it's a matter of the fabrication process, and we're going to discuss it a little bit later about it. We have to make all the connections. Of course, we would like to measure the electronics, the sensors we are basically embedding in our textiles, for instance. We have to test them, so we have to find the best way how to test the electronics and to test the textile parameter before and after the electronic integration. And last but not least, the idea is to not only find an application, but also verify if the electronic textile we were able to fabricate is actually capable to withstand the requirements of the very final application, as I reported here. For instance, this is a wearable device. It's a suit which is capable of monitoring human health parameters. So let's start from the basic, as a promise. We can define the textile fibers as the fundamental building blocks for all the textiles, followed by the yarn, which are basically a continuous strand of interlocked fibers made out of, for instance, natural or non-natural fibers. In order to make a fabric out of yarn, we have to weave, knit, or bond together natural or synthetic fabric. Last but not least, we have the garment level, which is basically an individual article of clothing, such as a dress, a suit, or all the sort of garment you can think about. Speaking about the textile properties, we do have to consider the wettability of the textile itself, which of course plays a very important role in the fabrication process of the electronics. Most importantly, the flexibility of the textile, because of course its capability of changing its shape and withstand multiple mechanical stresses, it's very much important, and we would like to replicate this property also on the electronics we're going to integrate in the textiles. Last but not least, the waviness and the roughness in general of the textiles. Of course, we have to consider that these textiles are not completely flat, are not completely smooth, and in order to fabricate on top of them, of course, the final roughness of the whole device is going to be strongly affected by waviness and the roughness of the very substrate, so the textiles we are going to use. Coming to the textile choice, well, of course, there's plenty of different textile platform we can think of. Here I just reported some fabrics in order to give you, a very brief idea. The most used one are the plain wave, I would say, and the non-woven, specifically also for like face masks and so on. But theoretically, we can integrate electronics in all of these platforms, let's say. We do have to consider two main categories for the very textiles. So we can start with the non-conductive textiles. Basically, we can consider them as an insulating materials made out of cotton, polyester, aramids, or all the other material we can make textiles of that basically do not conduct current, but also the conductive textiles. So nowadays, specifically, we've seen a growth in the market of these advanced fabrics made out of conductive yarns, metals and non-metals like silver, copper, or conductive polymers. Coming to the electronic design, I would like to briefly report here building blocks of a PCB, the most generic one, just to give you a quick recap of the very basic principle of the electronic design. So of course it's very much important to create a clear and correct schematic before starting the PCB layout and verify all the component connections and values. The path signals and of course its related width are very much important, because of course we would like to keep separate all the signals we are collecting, especially the DC and the AC signals, and of course the width of this paths. They do matter a lot, so it's always better to have larger paths for higher current. Of course, it's always better to not introduce sharp angle, otherwise we're going to create cracks and ruptures. Of course, it's a good manner to properly ground and separate the grounding with the power of the PCB, and to think wisely about proper thermal management of the electronics. Of course, how we're gonna be sure that everything is in place? Well, actually, it does exist a design of manufacturability, so with its own rule to check. So please do follow this let's say criteria, I would say in a word. Last but not least, of course, all the electronic we would like to build have to be tested, so they have to be capable of being tested afterwards. Apart from that, I would also wanted to report a little bit of a coding bullet point in order to give you a quick overview on the coding good practice, coding good manner, let's say. So first thing first, follow a modular design, which means basically keep it simple, or keep it as simple as possible principle. Try not to repeat ourselves, especially with variables, which means that basically all the variables should have one single task each. We have to keep it in mind that it's always better to have a structure in the code we're making, and we have to stick to this very structure, which means we have a responsibility principle, which function comes first, which function is above that or below that, which is who's the master, who's the slave, and so on and so forth. We do have to be consistent in the code we are making. So again, if we, I don't know, for instance, we are creating a while loop, a for loop, try to follow the same principle, the same rules we followed in all the code we are making. The code, of course, has to be reusable. Please do comment the code, otherwise the next person, the second user, is going to be lost in your very code. And it's always a good manner to handle the error from the very beginning, and to check if the presence of error and how to handle them during the let's say the program running. Again, testing and validation afterwards as always. So coming to materials, of course, we do have to divide materials based on their electrical properties. So three main categories: conductors, semiconductors, and insulator. And specifically, some of the insulators can be also used as planarization layer, but I would like to stress this out a little bit later. So speaking of conductors, of course, I do have to mention metals. As an example here, reported copper, not only because of its conductivity, but also because it is quite cost effective. I mean, way cheaper compared to gold, but also we do have silver, aluminum, titanium, and all the other metals we can think of. I would like to report here the carbon category, specifically carbon nanotube, as since it's become a thing nowadays, specifically for 2D application. Speaking of the last category I reported here, I would like to mention the intrinsic conductive polymer, and among the others, there's this very interesting P dot, not only because of its conductivity, but because if it well doped, it can be also flexible and biocompatible. Coming to the second category, semiconductors, of course, we can find some semiconductive materials, elements in the periodic table. So it has to be mentioned silicon, of course, but alongside with the germanium, and also some other compounds very famous, like gallium arsenide or silicon carbide. The second bullet point, I want to mention some metal oxide, and among the others, this very interesting semiconductive metal oxide, zinc oxide. And last but not least, it's worth to mention some polymers. So here I reported the P3HT, not only because of its quite interesting semiconductive properties, but also because of its sustainability. Coming to the last categories, of course, I mentioned earlier that we do need some insulating materials on the electronic point of view, but also it's worth to mention that specifically for smart textile, it's worth to have some sort of planarization layers in between the electronics we are fabricating and the very substrate we are using, so the textiles, in order to have a smoother substrate, in order to have a better deposition of the material you're going to use as electronics. Among the others in this very categories, so for a planarization layer, I would like to mention the TPU, so the thermoplastic polyurethane. As an insulator, electronic-wise, of course, we have to mention the broad category of metal oxide. Of course, among the others, one of the most famous is the aluminum oxide. And among the polymers, of course, it's worth to mention Parylene C. Again, as a matter of fact, not only because of its quite good insulating properties, but also because of its sustainability. Coming to the fabrication process, very much interesting. I would like to give you a very brief idea of quite all the possibility we can find on the market, let's say. One of the first that came to my mind is the dispense printing, which is basically based on ink, which is deposited by a nozzle on the very substrate, and basically the ink is pressed through this nozzle with this piston with a motor on top of it that push the ink down and allow the printing to happen. So basically there's a syringe. The great advantage is pretty much customable, so no mask needed in advance. The ink viscosity range is pretty broad, I would say. The thickness is very thick, I would say, in a word. So we can create very bulk electronics with this. So from 1 micron to 1 millimeter scale. The printing speed, it refers to the speed of the textile underneath, which is quite fast, I would say. The resolution is not that high, that low, sorry, so 25 micrometer, and it has the drawback of very low scalability, and it's slow, of course. I've reported here a very nice video showing how does it work. So basically, you can see the ink push through the syringe and printed on the substrate here. In this very case, we're printing silver layers. Coming to the next one, I decided to report the screen printing, which is based on this screen in which the ink is forced to pass through this the screen lattice. So in this very screen, we can find, let's say, a matrix, a lattice form, very porous, and where we have our design, of course, the porosity changes and the ink is allowed to pass through and have the final printed image. So as mentioned, we need a squeegee to put some pressure on the screen and to push the ink through the holes of the screen. It's a flat and rotary based process. The ink viscosities, of course, is very much related to the let's say the porosity of the screen itself. The thickness, it goes a little bit down here, so it's an advantage, down to 3 micrometer, quite interesting. Is a good fabrication process for thicker layer, so above 10 millimeter, so giving multiple layers of printed ink, we can achieve thicker layers. The speed, of course, is not available because we don't have any textiles passing through it. It's firmly retained in position, and the resolution with special mask we can go below 20 micrometer. And of course, the scalability is medium-low. It's not very scalable. I decided to report it here, another video. So as you can see here, we have our substrate that goes below the mask. This is the very mask we would like to use to print the electronics. We have a blade, a metal blade that spread the ink around. It's a silver ink. And then we have the squeegee that applies a specific force and force the ink to pass through the holes. And this is the very final result, as you can see. Coming to the next one, another very interesting one is the yarn coating, which is basically a very yarn which is forced to pass through this syringe and this nozzle. In this syringe, we find a conductive, semiconductive slurry. Here, after the passing through the syringe, the coating happen, and of course, as you can already understand from this very schematic, it's not very selective coating method. Is very much ideal for scalable production. The viscosity is pretty low. The thickness we can achieve up to 100 micrometer thick, of course, is related to the gap between the very yarn and the nozzle. So the speed is pretty slow, I would say. The resolution is not available, as I said, it's not selective at all, but is very scalable. And of course, I've reported here again a nice video. So the thread yarn is passing through the nozzle here. We apply conductive ink, which is collected also in the syringe. This is the heater for the annealing after the coating. And as you can see here, we have the coated yarn. This is magnification. There you go. And this is basically it. So the yarn passed through the heating system and is collected with this rotary system. That's it. Very simple. Another fabrication process I would like to mention is this ink jet. It consists of a direct write method suitable for inks with low viscosity. So the ink is ejected by a nozzle onto the textile substrate. It's basically the same printing system we see on the printing for A4 paper, basically. It's exactly the same. The viscosity, as I mentioned, is very much low. The thickness is quite interesting because it can go down to 0.01 micrometer. It's not very fast, I would say. The resolution can go down to 20 micrometers, so very thin and very accurate, I would say, in the design process, and it's quite scalable. So it's again, it's with a scanning printhead, we can achieve high scalability. Another, the final actually fabrication process I would like to mention that I personally investigated during my PhD is the sputtering process, in which basically we have an high energy ion bombardment into an argon environment, I would say, under vacuum conditions. Basically, the bombardment of this argon ion on the very target material cause the atoms or the molecules, it depends on the material of the target, to be ejected from the very target, from the surface of the target, and to be transferred to the substrate on top of which we would like to deposit our material. And as I said, these particles basically they travel all across the chamber onto the substrate, forming a very thin film. The sputtering technique can be DC, RF, or magnetron. The thickness is very interesting because we can have very thin layers of material down to 2 nanometer. The resolution with of course, the photolithography process can go below 5 micrometer. The little drawback of this technique is, of course, it's not very scalable. Coming to the encapsulation, I decided to report here just one method that has been investigated in Steve Beebe group, but you can find there's plenty of this encapsulation method in the literature. just for the, I decided to report this here because it's quite interesting and quite peculiar. So it's based on a TPU coating and a heating vacuum forming process. Basically, we have an operating window on top of which we have the TPU film. This is the very flexible circuit. We apply infrared radiation, heat, basically, and with the vacuum applied here between the TPU and the very substrate, we can change the TPU form because it was kind of melted, and give it the final shape of the flexible circuit we are using. It's a quick and efficient process. The improvement it improves actually the circuit robustness, increasing the number of bending and washing cycle. Of course, there's a little drawback. So, for instance, if we would like to use, let's say, a humid sensor embedded in the very flexible substrate we are using, of course, we have to think about something else rather than using a classic TPU, but something that is that can let the specific parameter we would like to harvest or investigate to pass through the encapsulation system. But of course, it's a way to protect our own electronics. I would like to briefly mention some connection and ways to create connection. So, of course, the easiest one is the thermal joining. One of them is, of course, one of this big family of thermal joining is the soldering. Of course, is a matter, as I think the majority of you is aware, is a matter of add an additional material with a lower melting point called solder to the electronic circuit. Of course, by heating, the soldering melts, and through a wetting process, it attaches to the PCB, to the contact pads, to the electronics in general we would like to contact. Of course, the solder can be an alloy made out of tin or lead, which is basically replaced nowadays by silver, copper, or zinc alloys. Another very interesting and of course it's textile-based in a way is this conductive hook and loop, which is commercially named after Velcro. Is a fastener that comprises hooks and loops. So on one side we'd have a connector, and on both sides we have connectors that can basically connect to different textiles together. It's funny because it's a thing that was discovered in the late 1980s. It applied for electrostatic shielding and electrical contacting, and it's very much interesting that fact that you can find on adafruit.com conductive hook and loop, super cheap. So if you would like to try one of them, and they're quite interesting because they can survive up to 5,000 opening and closing cycles. Another very interesting everyday, let's say, thing we can find on the market are these conductive zippers. Was actually a discovery in the 1953, the first electrical zipper. They made a pattern out of it. It's basically a conductive and insulating teeth alternate each other. So each element tooth comprises a conductive area which touches the other conductive area on the other side. The final one is these magnetic connections. They were introduced into the market as breakaway electric cords for deep fryers, for instance. The magnetic connectors disconnects, of course, for safety reason when the cable is pulled. And of course, there's a master modules responsible for initializing the slaves and centralizing the data. But it's a very simple, let's say, connector. So coming to the summary of this very first part, today we find out a way of define electronic textiles. Specifically, we dig a little bit deeper into all the materials and all the possibilities of developing our own textiles. We rehearse a little bit all the good practice for design and coding, the electronics we would like to build on our textiles. And last but not least, we discover all the possible fabrication process and connections, way of connecting electronics available on the market. Last but not least, I would like to thank you all for your very kind attention and see you in the second part of this educational lecture series of Team Nano. Bye!